Okay, so today's class, I'm going to do a part of the class is going to be on trajectory generation in CoppeliaSim, and that is going to be using the Reflexess motion library, which I've briefly talked about but never really used in MATLAB. Uh, the two commands we'll be using here are RMLpos and RMLstep, as I will show you, and then I will show you how to use the user-defined variables. So for example, in this case, I'm trying to track a joint reference position and I want to plot that in the graph. How do I do that? And that's going to be the second new part in today's lecture. So I already have ready to go file this as the simple pendulum with a zero position at vertically downward position. If you let this go, it swings passively. And my goal here is to try to get this pendulum to go from the 90 degrees position to the 0 position, but I will specify a reference trajectory instead of just getting it to go from 90 to 0 using a PD control. Okay, and I'll show how RMLpos is used. Okay, so first things first, let's just work on the script. I'm going to get an object for the joint in this case. So joint equals sim.get object handle joint. Okay, now some of the things here I'm going to show you about using the RML object are things I got from the documentation. So I'm going to open that first. So let's go to CoppeliaSim reference API. Here I'm looking for RMLpos. Okay, so that's one of the commands. Okay, so I'm going to be using this command. It's a really long command. It's right here. Okay, so what it does is basically it helps you to go from the current position to a final position when you can specify the velocities, you can specify the accelerations, that is the maximum velocity, maximum acceleration, and you can also set up other things. So let's just understand this command. Here it is. Handle RMLpos, number of DOFs. So you can specify not one single link, but you can specify 5 links or 10 links, whatever you want. In this case, I'm just going to do one link, the joint of one single pendulum. Time step, the recommended value is 0001. Then set the flags to -1. Then you specify the current position, velocity, acceleration. Okay, so that whole thing is going to be one big array. Okay, it's not separate. Then you specify the Maxwell jerk. Then you specify selection matrix. I just going to put a non-zero value. And then the target position velocity. So you want it to go to a certain position velocity. In this case, it's going to be 0 position with a velocity of 0. And then the auxiliary points. Just not get too much into the auxiliary part, but let's just copy paste this in here. Okay, it's really long. Okay, handle. Now this handle is different from the handle we have for joints. This is going to be a handle for the RML object, and you'll see what I mean by that in just a bit. So I'll just call this RML object. DOFs, as I said, well, let's just copy that. It's much easier if I copy paste these things. Okay. Okay, so let's comment these things. Not this one, not this. Okay, let's start. Number of DOFs, number of joints. So it's in this case just one. The smallest time step. They recommend just put 0.00001. So I'm just going to copy paste that. The flags. Here the flags corresponds to -1. Let's just put -1. Okay, now current position, velocity, acceleration. Since this pendulum has well, a single joint, I need to specify one position, one velocity, and one acceleration as a table. So the position here happens to be, if you click here, you can see that the position is actually 90 degrees, but and I can put 90 degrees, but what if you start the pendulum at a different positions? What I'll do is, instead of specifying the position as 90, I will get the position. So I'll say position equals sim.get joint position joint. So this will give me the position of the joint, and just keep it updated. So that's the position. So position. Now velocity and acceleration, I just go to specify 0 and 0 for the velocity and acceleration. So this is going to be, as you can see, for each joint you have 3 variables: position, velocity, acceleration. And accordingly you'll have to, if it's 2 joints, you're going to specify position 1, position 2, velocity 1, velocity 2, acceleration 2, and so on. Then you need to give a Maxwell acceleration jerk. Okay, now this is something which we'll again just make up something. Let's say the max velocity is 1 radians per second and 0.1 for the acceleration, and it also asks for jerk, I think, which is the rate of change of acceleration, so 0.01. So this is just a ballpark, just to give it 1/10 of the previous one. That is because the time appears in the denominator, and you just basically, what you do is you basically scale it by the time that way. Okay, next is selection. One value for a default behavior of fill the vector with non-zero values. So really here it doesn't matter. I'm just going to put 1 or 2, whatever you want, and then target position velocities. This is where I need to specify the end position and end velocity for each joint. So in this case there's just one joint, so end, let's say 0, right? Here it's at 90, so and I want it to go to 0, so it's going to be vertically upright, and then vertically downwards position, and then a velocity of 0. Okay, so that is my RML object. Now once I have the object, I then need to, what I need to do is I need to call this object. So this is initialized, I need to call in the actuation. So each time I call this, I need to step through the RML object and get the new value for the joint angle, use that to set the target joint position, and so on. And so what I mean by that will be clear in just a bit. So what I'm going to do is I'm going to use the RML step. So if you look at the command for RML step, it's right here. Let's copy paste the command right here. We'll put it here. Okay, let's see what it actually means. Okay, it's not too bad. Okay, now let's see. We want to set, well, here we have the number handle and time step. So the number handle is going to be, now this is not the joint handle, it's only going to be the RML object. Okay, so that's object. So it basically is a method, a function, which will give me what is the next position from the current position, and the next one, and so on. So it's called in a loop, so it's giving me the new position I want the joint to go, and then the next one, and so on. Then I need to specify what is the time step. Now here the time step, the best way to get the time step is to actually give the simulation time step. So to get the simulation time, the command is sim.get simulation time. Okay, there it is. So this is basically a function which just gives you the simulation time. Okay, so if you go 50 milliseconds, which is what it is, it will be 0.05 and 0.1, 0.15, and so on. My bad, I think it's 0.05 005, 01, 01, 0, 0, 1, 5, and so on. You just see iterates that way. Okay, so that's, we got that on the right hand side. Now let's see the left hand side. Result. This result is basically should be a is it over here, time step? I don't see the result. Okay, let's see. I might have not copied that. Where's the return value result? Interesting. It doesn't give what that is, but usually the first argument is tells you if something worked or did not work. So usually if it's nil, then it did not work. If it's not nil, then it's worked. So let me just call that result. We will take that data. Now this one is the pause val acceleration. This is basically giving you the new position, velocity, acceleration at that time step. Okay, at that gate simulation time step. And then the number synchronization, we don't care about that, so we won't worry ourselves with this. Okay, so this variable here will be such that new pause val accel is such that we have the position will be the first value, velocity will be second value, and acceleration will be third value. Okay, in this case I'm only going to set the position, I don't need this. And so once I have the position, which is the first value, I just need to set the joint target position. So sim joint target position set joint target position. Okay, that's good. And then I need to give the handle. So in this case it's going to be joint, and then I need to give new pause val accel 1. Okay, so this is giving this value here, and then it will be set. Now one thing I've not done so far is I need to set the pendulum to be in position control mode, otherwise this won't work. So let me go here and to joint, torque force is fine, enable the motors, control loop enabled, and then set this to, I don't know, let's set it to 100, 10, just setting it something. Okay, I think we are set. There's a problem. One of the function argument is not correct, and that is line 4. Okay, let's see this command. Get joint position. Get joint position. Okay, that's the syntax. Okay, looks okay to me. Okay. Okay, I have no idea why this is wrong.
Is it that you just need like the handle and not the quotations? Yeah.
Right, perfect. Thanks. Okay, now something else is wrong. 16. One of the function argument is not correct. 16. 16. Okay. See, RML. Okay, so DOF's position, Maxwell. DOF's is right. Smallest time step is correct. Flags is -1. Current position is fine. I hope that is printing the right thing. We can check that. We can just say print position. Then we have so position, velocity, acceleration. That's the current one. Maxwell acceleration jerk. So 1, 2, 3. There are 3 of these. Then we have target, position, velocity. So selection is 1. Target, position, velocity is 0, 0. Aux data. I think I can ignore that. I can ignore whatever is the end. Okay, I didn't seem to have changed anything, but let's see what happens. So the position printed out, so that's fine. Something else is not right in 17. Okay, my notes, I wrote something like this. This is from my notes. Okay. Apparently, is that it? I don't know. Maybe that's what it is. Okay, so now it proceeded to 34, which means this is fine. So I apparently need to give this as a array. Okay. Okay, let's go to 34. It says a nil value. Okay, so this printed a nil value here. New, so print new pose val exit. And so if you print that, it gives you a nil value, which is seen over here. Okay, so let's see why it printed a nil value. Okay, handle, which is right, time step. Wait, this is. Did I copy the wrong thing? RML step. Okay. Okay, let's copy this here. Did I delete the other one? Oh, my bad. I think it's everything looks right. Cycle time. Okay. Okay, it all looks fine. See, okay, I just forgot to copy the syntax. Let's see, copy the syntax. It's right here. Okay, result table synchronization time. So don't see a problem there. Number handle, it should be this one. Sim get simulation time. Is this right? Let me just check if this is right. I can just say print and run this, and then it printed 0, which is right. The time is 0. Okay, so RML object, that looks okay to me. Okay, I think I need to first understand if result prints right. Result, sorry, print result. Okay, I suspect that has given me a value of nil. Oh, it's -1. Interesting. Okay, so per my notes, the -1 is not a is not a good sign. It should be 1. Uh, if it's 1, let me just write it down. It's not in the notes. So 1 or -1 for result is bad. Okay, and then anything else is good. Okay, so we got to figure out why it's giving this. Okay, per my notes, have this is what I have from my notes. Interesting. Okay, so I shouldn't be giving the simulation time, but it's just a simulation time step. The simulation time step is different from time because it's basically gives you the increment, so it's going to be 50 milliseconds. So that apparently was a mistake. Okay, let's see if this works. Okay, so it's doing something, it's moving. Okay, so now what they recommend here is really this looks like it's working, but here's what we need to actually do. What we need to do is we need to say we need to destroy these RML objects if we're not using them. So what we say here is if result equal to 1 or result equal to -1, then sim.rml remove RML object. We just get rid of it. And then there are good practices actually cleaning up the stuff. So we basically say if I'm just going to copy paste this. This is some syntax I got from CoppeliaSim. If RML object exists, then you clean it up. And then so okay, I think that's about it. Okay, so now that we've got it to work, and you can see that it's let's see what the mistake looks like. RML remove arguments is not right. Okay, what's the problem now? Line 37. Oh, here it is. Object. Okay. Huh. This is line number 43. It doesn't have that. Okay, so let me just clean it up. So if result is not equal to -1, then it's only then I would set the target position. If not, then I will not set it. That's kind of important. Okay, so we'll do this and I hope it will work now. Interesting, start moving because it's never really going in here. Okay, let's see what mistake I did now. Okay. For a second, let me just get rid of this. Seems like this code introduced all the problems. Let's just try to comment this out for a second and see if we can get it back to work back. No? Oh, there it is. It's working. Let's move this. You rearrange it with that. We can do both. Okay, stop. Okay, so clearly this part is causing the problem. Okay, it stops. So I believe every call to actuation, it goes to sensing. Sorry, oh, we're putting in sensing. My bad. This is really bad. I should not put it in sensing. I should put it in cleanup. The cleanup is executed after all the code is quit. So if it's put in sensing, then it's sort of cleaning, it's removing the object every single time. So now it shouldn't have a problem working. So it works now. Okay, so that was an error where I put it. This should all work now. Move. Okay, that works. Okay, so the right way to do this is with everything included is to actually only call this loop if RML object exists. So if RML object, then do this, do this, do this, do this, do this, this, and then enter. Okay, just like this. If RML object, then only destroy. Don't destroy it otherwise. Okay, so let's just check it once. Okay, it works. Okay, now we saw that it's not really up to the mark. It's basically very shaky. Okay, and we would like to see how it is actually doing, right? So we create a new graph, and on the graph, let's choose joint position. It's joint, okay, and then give it angle, and then give it color. It's red. Let's it be red. And so if you run this, you can see that it's jagged. It's not quite what you want. But then we want a reference to compare this against, right? So how do we get the reference? Now, the thing about a reference is that if you see here, you can only add a data stream correspond to one of the objects. How do you create your own variable which you can plot? So it turns out that at the end, there is something called various user defined, and that can be used to create whatever variable you want. So let's just do various user defined. That's going to be user data, something which we define, and say okay. Now we can name it anything we want. So let's just call it reference. Okay, and now, well, first let's change the color to say green. Okay, and now what we'll do is we'll set this variable in code, which is called reference. For that, we need to go and see what documentation provides. So if you type graph, set graph, set graph user data. I think this is the one. Sets one value in the user defined graph stream. Okay, so we need to use this command where I'll just put what it means. It does. So if you go to code right here, we need to specify it. Let's just specify it. So what I'll do is I'll basically specify it to be this value, right? it needs to be the reference position. So the best place to specify it is probably right here. Okay, so let's see how to do this. Let's just go back to the syntax and see what we need here. Okay, so we need to set the graph handle. So the graph handle is basically the handle to the graph. This is this. So we need to refine that previous to using it. So graph equals sim.get object handle graph g caps. Okay, and then let's use it here. Graph, and then data stream. This is going to be the data stream we created. User defined. Okay, so in this case I believe we've called it a reference, so let's use reference. Okay, and it should be a string, so it should be in quotes. And then the data. Now what we want that reference to have, well, we want it to have this value. Okay, so if everything works right, we should see it move. Okay, so now there's a problem. You can see that the green line is very close to 0, but the blue line is, or the red line is hovering here. Now the reason here is because the way this works is anything over here in the graph is in degrees, but the reference unit we have is actually in radians. So if you wanted to plot on the graph, we need to convert that to degrees, which from radians. So what I need to do here is, let's take this and convert that to degrees. Let's see, position reference in degrees equals that times 180 divided by math.pi, and then I just need to put the reference in degrees, and I think that will work. Okay, so this is now showing you the response. You can see it looks, well, it's actually not good because it's shaky, and also you can see it doesn't quite go to 0. It's hovering around 0. Let's just stop this. Let's rotate it a little bit. So, better. Okay, we run this. You can see it's the way it's performs. Okay, so the way this can be done is by tuning the PID controller. And if you go to PID here, I set it to 110 for the D. You really don't need such a high value. Just put 1 and 0. 1. This is just a proportional controller, and then see what happens. Okay, clearly it's doing a very good tracking. Now one thing here is, if it's doing the right tracking, you might want to know what is the torque at the joints, so, or the torque at the motors, which the motor is applying. You only know the set position, and so it's sometimes useful to know the torque, because you can use that torque. That can be one of your measurements. So there is a command called joint force, I think, get joint force. Okay, so if you use force or torque get joint force, it will actually give you the torque at the joint. So for a linear joint, it's going to give you the force. If for a rotary joint or revolute joint, it's going to give you the torque in Newton meters. So we just take that and paste it in wherever we want the torque. So let's say we want the torque right here. So in this case, the torque, and then a handle for that is going to be the joint handle. So you can say print torque. Okay, now it should print the torque here. Then I'm printing. Just comment this out. Okay, now run. Okay, so what you see here is the torque. Okay, and I'll stop. Well, when it goes close to 0, you can see that the torque is almost 0, right? It's 1e negative 15, which is 0. So the torque required to hold it in the vertically downward position is clearly 0, and so that basically is one way of checking if that value makes sense. The other thing which we notice here is we can see that these PID control gains are really something which you need to work on, right? 0.1, let's try 0.1 and see what happens. There's a tracking error, as you can see. Now, if you could have also, by the way, plotted the error, maybe that makes more sense. So if you can go here and I won't do it, but you can just say instead of plotting the joint reference, you can plot the error and see how much the error is changing now. So clearly this gain is not, well, 0.1 is too less and 0.1 is too high. If you go here and then I guess let's make it 10 and see what happens. So 1 looked pretty good. That one also gives an error. Okay, so the next part in the course is actually about why did it change? Okay, so 10 is not good. 10 is not good. Try 1. It's a little better. Okay, the right way to do this is actually plot the error, which can be plotted as a user-defined variable. Okay, I'll stop. So the next